You just asked me about 9 on this take-home quiz. It says this. It says find the area, and then you got to watch this language. It says inside r equals 3 minus 3 cos theta, but outside r equals 1 plus cos theta. So, you know, depending on who you are and what you know and what you do, I guess maybe you would pick up a graphing calculator, put it in polar mode, and try to sketch the graph of these things. And I could do that. Maybe I should do that to show you how to do that. But I kind of know about these graphs, so maybe I don't need a graphing calculator myself. I could plot points. I mean, a graphing calculator will help you. You need to see these. You need to see this picture. And then my other advice is you don't work off that little. You use your graphing calculator to help you get a little picture, but trying to work off that little screen might not be too beneficial. And I would blow up a picture on a piece of paper or on a whiteboard and see what's going on. This first guy, I think both of these are cardioids. And this first one's kind of big and maybe goes this way. So I think I just figured something out. Am I right about that? I think that's r equals 3 minus 3 cos theta. I could supply a few details here, but I think that's kind of it. Then this guy is the other one. If I use another color, that might help. This guy is sitting the other way, and he's a little smaller. Cardioid like this. So you guys okay? So I think I got a decent picture here. 1 plus cos theta. And you know, you might see something like that on your graphing calculator, but again, depending on the window and that little screen, it doesn't show up that good. So maybe you got to zoom in kind of, and again, maybe, you know, use your own paper to draw your own blown up kind of graph, and then, you know, kind of exaggerate it maybe, to exaggerate things a little, maybe to see things. Boy, what do they want? Inside the big one, all right, so inside this one, is that what? But outside the blue one. So, you know, inside the big one would be all this stuff, but since they say, but outside the blue one, that means I don't want these. I don't want these. I want to be outside of these, yet still inside the big one here. So I think I just figured it out. I think it's this area. Inside this one, but outside that one. I mean, the language isn't that confusing. It's very logical, actually. Inside that one, but outside the other one. So there you go. You know, you know, I could work on kind of the upper half of this and double it is kind of one thing I see. I could kind of just work on the upper half of this area and double it. I think what might be important is sort of this point. And that point isn't really a point, it's sort of an angle. I think I want to find that angle where these two curves and then I think that's where they intersect, don't you? Yeah. So it's where the blue one intersects the black one, and I think I should maybe just set them equal to each other and do this math. The other day we did something similar to this, and we got kind of a nasty angle. Let's see what happens on this one. Yeah, this might be nasty again. Well, maybe not, maybe not. Let's see, if I add the 3 over here, that's 4 cos theta. If I subtract the 1 over here, that's a 2. If I divide by 4, yeah, this is actually going to be nice. So I set them equal to each other. I'm gathering like terms together, solving for cos theta, and when cos theta is a half, that's a very famous angle. That's a 60-degree angle. Your calculator would tell you that. A 60-degree angle, though, sometimes I talk in degrees, but when you really do the work, you better be in radians. So a 60-degree angle is pi over 3. So that's that angle. By the way, it's that pi over 3. Here's the other point of intersection. Is this negative pi over 3 here, I guess. Negative 60 degrees here. But I don't think I'm going to bother with that since I'm going to work with this top half, I think. So I just discovered this is pi over 3. All right, so I think I want to integrate. I want that black area there. I think I want to integrate from pi over 3 to pi. Well, and then double it. I mean, there's a couple ways. That's what I decided. I kind of think, you know, there's a half in front of this integral. Maybe we need to have this area formula kind of memorized. It's 1/2 the integral from alpha to beta. It's the function of theta squared d theta. That function of theta, by the way, is r. R is a function of theta. So here we go. We got a 1/2 out front. I think I'm going to go from pi over 3 to pi. I think I'm going to double it. And
is there a reason always when to double it and not to double it?
Not really. I need all that black area, and I sort of used a decision that if I just go from pi over 3 to pi, that'll be half of it. So I think I'll just do half of it and double it. I just made that decision. I
don't know if there was a reason to use it and when not to use it.
Yeah, I don't know. I'm not sure if I got a good reason. If I see symmetry, sometimes I tend to use it. It might help the calculations be a little easier, but I'm not real sure about that. If that's really true. But you do see the symmetry, right? I mean, that's not eluding your vision, right? From pi over 3 to pi would be half of what I actually want. So I think I'll just do that and double it. Listen, you guys remember, I lectured on this last week. I talked about how this is not about top and bottom rectangles anymore. This is about sweeping out sectors of area that emanate from the pole. I want to draw a little picture here. I would be sweeping out sectors of area like this. You know, so what I'm going to get if I do this, if I just integrate that black function out there, I'm going to get a lot of area I don't want. I don't want this white stuff here. So I think what I need to do is, is subtract the outer curve minus the inner curve. So sometimes this formula is not this formula. Sometimes this formula is 1/2 and it's some outer function of theta squared minus some inner function of theta squared, d theta. And again, back in our old rectangular coordinate days, we would do top curve minus bottom curve. But this ain't top and bottom. This is outer minus inner. Outer minus inner. So I'm ready to set this baby up. I think I see the outer curve is the 3 minus 3 cos theta. I want to square him minus the inner curve, 1 plus cos theta squared, d theta. And sometimes the test question, or the quiz question, or the test question says, set up the integration to find the area. And if the question was set up the integration, we are finished.
Wait, we want to find the area all on the black, and this would just give us the area of those two.
Oh no, I multiplied.
With the little sliver on the other side.
Hold on.
We're going from pi over
So if I'm going to go from pi over 3 to pi and double it, I'll get all the black area. And all the way from pi over 3 to pi, I will be sweeping out sectors that contain a little bit of white area that I don't want. So all along that integration from pi over 3 to pi, I will be doing this subtraction. I will have outer area. There's a lot of outer area I'm going to get. but I'm going to have a little bit of inner area that I don't want. So I'm going to be subtracting from pi over 3 to pi, outer minus inner. Outer curve minus inner curve from pi over 3 to pi. Double it to get all this other stuff down here. So it's a new way of thinking. I mean, you draw these pictures, the pictures are new, and then sweeping out area, sectors of area is different than adding up rectangles of area. We're not adding up area along the x-axis. We're doing this with respect to theta as we rotate around. It's a different game, but you can, so just thinking it through to set it up takes some different type of thinking. But here we are. The setup is over. Doing it is, kind of is another issue. I mean, that's another issue. That's a lot of work to do it. I feel like drawing and thinking this new way in polar coordinates is sort of what I really need to help you with, but I probably need to help you with doing it too. This one's a tough one. Let's just look at the question. Did the question actually want me to do it?
Yeah.
You're right. It says find the area, so they do want me to do it. Again, look for problems that don't. Number 12 and 13 both say set up the integration to find the area. So those, you get to stop here. You set it up and you can stop here. But you do have to do a few, I guess. Apparently we got to do this one. I mean, what does that mean? Foil it out, collect like terms, and integrate and evaluate. That's what it means. When you do integrate, you'll hit a cos squared in there, and when you integrate a cos squared, you have to recall our old half angle formula. So we've talked about that a couple times over the last few days. Should I help you finish the whole thing?
Sure.
Absolutely.
I like these ideas. These ideas are important. The construction of the integral, the setup of the integral is so important. That's what I mean. And then I feel like I don't really need to help you with the rest, but I know I kind of do. But I feel like this beginning stuff here, this setup was real important. In order to do it, then this is our integral. We're working on this integral. The 2 and the 1/2 cancel. So it's pi over 3 to pi, and then I am going to FOIL that out. 9 minus 18 cos theta plus 9 cos squared theta. I think when I FOIL it out, I think I did that right.
Yeah.
And then when I got to FOIL the other one and subtract it, I'm going to do that all in one move. That'll be a -1, a -2 cos theta, and a minus cos squared theta. I FOILed it, and I distributed the negative sign. And then I can combine some like terms. So this is really an 8 minus 20 cos theta plus 8 cos squared theta. I just combined some like terms there. I could start integrating, but let me hold off a second. I'm going to use my half angle formula right here. This is 1/2 1 plus cos 2 theta. If you distribute that 8 times that half, well, that's a 4. And if you distribute it, it's a 4 plus 4 cos 2 theta. You could gather the 4 with this 8 out front and call this 12 minus 20 cos theta plus 4 cos 2 theta. I think I've done a good job. Now, don't forget, I've done all this work. I still have not integrated. But I think I've done a good job foiling, combining like terms, doing my half angle formula right there. I mean, I've done a great job. I'm patient. I don't freak out. Just calmly foil it all out, gather like terms. But now I think I'll integrate. Anybody know how to integrate a 12?
Theta.
12 theta, she's right. How do you integrate a cos theta? I think it's just a sine theta. So it's negative 20 sine theta. Okay. Let's see, how do we integrate a cos 2 theta? I guess that's just a sine 2 theta.
And then you have a
but it spits a 1/2 out front
So it's 2 sine.
because you do a little U substitution. So it spits, so you get 2 sine 2 theta. And there's no reason to do any identities now. We're done. We just have to evaluate with these bounds from pi over 3 to pi. This is fun. I appreciate you guys making me do this. Maybe to finish it, I'll move right over here. So to finish this, I'll plug in a pi. Of course, that's 12 pi. The sine of pi is nothing. The sine of pi is a 0. And then the sine of 2 pi is a 0 when you plug the... So there's a bunch of zeros there. But now we're plugging in pi over 3, so things will be a little different maybe. Here we go. Now we're plugging in pi over 3. Let's see. When you plug in pi over 3 right there, that's a 4 pi. Pi over 3. The good old sine of pi over 3. I guess that's square root of 3 over 2.
Oh, yeah, that's right. 60.
Your calculator would tell you that, except it might tell you a decimal version of that. But it's the sine of 60 degrees. It's the square root of 3 over 2 times 20. Square root of 3 over 2. And then, here we go, plugging in a pi over 3 here. Well, it's multiplied by 2, so it's a 2 pi over 3. Well, that's 60 degrees over in quadrant 2. I'm doing this in my head. I got a unit circle in my head. Have you seen the shape of my head? Got a unit circle in my head. I'm plugging in pi over 3. It's 2 pi over 3. That's 60 degrees over in quadrant 2. Yeah, sine's positive over there. That's just square root of 3 over 2 times 2. I think I did that right. I think I did that right. The problem is over except for a little cleaning. The 12 pi minus the 4 pi is an 8 pi. And this is negative 10 square roots of 3. But this is plus 1 square root of 3, so together that's a negative 9 square roots of 3. Dude, that's the area. Dude, that's the area. And that was my number when I played high school chess team. I'm just kidding. We couldn't afford chess boards, chess pieces in my high school.
Yeah.
Yes.
You have a minus in front of parentheses, would that make it?
Oh,
Plus?
there's a minus in front of these parentheses. What a jerk.
No,
So that makes this plus, is that what she said?
I think
Yeah,
so.
see, that wasn't my number. I knew that wasn't my number on the high school chess team. Yeah, she's right about that. Thank you. I lost this minus sign.
Yeah.
I kept it for the 4 pi. I subtracted the 4 pi,
Yeah, you did.
and then I lost it for a second. Thank you.
Golly.
This was on your take-home quiz, right?
Yeah.
So now I just helped you with it? All right.
I have a question about number 2 on the take-home quiz, especially when it comes to the bottom, like when it ever says makes one revolution as t varies from this to that.
Yeah.
I don't exactly understand
I know.
what they're talking about.
I know. All right, so I can make up a new one, or I can help you with that one, but when it says, here we go, when it says it makes one revolution, you know, I guess sometimes I like to say it makes one revolution in 20 seconds. But the problem is there's really no time. There is no units on these problems. These are math problems without any physical measurements like seconds. So instead of saying 20 seconds, I'd say as it makes one revolution as t goes from 0 to 20. Anyway, that's just a different way of saying it, but leaving off any units. But now what? That means I wanted to do one revolution as t goes from 0 to 20. Now, guess what? The time it takes, and here I am saying time again, but the time it takes to do one revolution is called the period. So basically I'm saying the period should be 20. That's what this says. This says the period is 20. That's what this, so I'm going to help you with this because this does confuse students, but this is saying that the period is 20. Now here's the other thing I know about period. The way I usually calculate period is I take 2 pi and I divide by that coefficient in front of t in a trig function. In a trig function, we usually have this, what we can refer to it as anything we want, but it could refer to it as omega t. And the way we calculate a period is we do 2 pi divided by omega. I'm off camera here, sorry, I forgot about that. Off camera, baby. All the best stuff. Whatever happens off camera stays off camera. Is that one of the things they say? If it makes one revolution in 20 units of time, the period is 20. But when we calculate period from a trig function, don't we take 2 pi and divide by omega? That number, that coefficient in front of t. So now put these thoughts together. In other words, I'm searching for this omega. And apparently 2 pi over omega is 20.
So at what point do we bring the omega over to the period?
Now. I mean, now you're searching for this omega.
Yeah.
Is what you're searching for. You want the coefficient on t that makes this happen. It's not 20. It's not 2 pi. It's calculated through this little bit of work here. The period was told that they told you they wanted a period of 20. Normally when you calculate a period, this is what you do. So put those two thoughts together. I'll multiply by omega. I'll divide by 20, and I'll calculate, do a little algebra, tells me my omega is 2 pi over 20, or pi over 10. And if I put that coefficient on my t, then I've created a trig function that has a period of 20. Right? It's awesome. I've created a trig function that has a period of 20. You needed that on Friday's quiz. You needed that knowledge. And I just made this one up. You need it on the take-home quiz a couple of different places. You need this idea. I know it gets students. I know it does. But after I explain it a couple of times, it sure is. It's easy, but it takes a little thinking through this process. The knowledge of what's a period and how to calculate it.
So is that faster? Getting it at one revolution, or is it? I'm thinking that.
So, what are you asking me? If it's
I'm asking if it'll make a revolution faster. No, it'll be slower.
then what? Right. So she's asking, is this particular situation? And by the way, I'm referring to a generic trig function here.
Yeah.
In our specific problems, we are talking about parametric equations, and so there is probably an x and a y, but the idea was for both of them, we just calculated the omegas for both of them. You know what I mean, you guys?
Slower.
I mean, I was just sort of
Yeah, this
halfway doing the problem.
Will they always have the same omegas?
They, right, the ones who don't have the same omegas, they're weird. Yeah, they twist around on each other. We looked at one with a graphing calculator. We played around and looked. They're pretty, anyway, what I'm usually asking you for here is a circle or an ellipse. And they have the omegas should match, right, right. So I didn't specifically help you with 2, but I helped you with the concept, right? And so, that, again, that happens to you a couple times on your take-home quiz, and it happened to you on Friday's test, quiz. So maybe this little lecture will help. How to find that omega. You know, the other way, just to make it trickier, watch. Just to make this a little trickier, sometimes I say this. It does 6.5 revolutions in 15 seconds. I mean, now I'm really messing with you, kind of.
Yeah.
I'm trying to make it more complicated, but well, what you really need is the period.
Yeah.
And the period is the time it takes to do 1 revolution.
Right.
And so I'm sorry I screwed with you here. But I kind of like, I think of it like this. If you do 6.5, what I do is I make like an equation. If I do 6.5 revolutions in 15 seconds, then, and I want this to be 1 revolution, what should I do to make this a 1? Divide by 6.5?
Yeah.
Divide by 6.5. So then 1 revolution will be, right. I mean, anyway, it depends on how you think. But if 6.5 revolutions is 15 seconds, then divide by 6.5, right, to find out what 1 revolution is, right. Dividing by 6.5 ain't real pretty. It's 13 halves. When you flip that up, it's 30/13ths of a second.
And then do you do 2 pi divided by that?
Well, yes, because, well, no, not 2 pi, no.
I mean, I'm sorry.
Well, maybe.
No. It's 2 pi divided by omega equals that.
So again, you're looking for parametric equations that do this. So you're looking for the omega t is really what you're looking for.
Right.
And
Okay.
2 pi over omega is
Equals
the
30.
period, and the period is
30 over 13.
that number. Right. So now we can find omega. Do
26 pi over 30?
good, or 13 pi over 15 if you reduce it.
That's so 2 pi
Cool.
divided by that. Yeah.
So as nasty as the numbers might be, you can do it.
Yeah.
That's awesome.
Yeah.
I like those problems. But what other kind of questions do you have? Any other good questions? All right. 6. Somebody said 6.
There's also a number over here.
Somebody said 8. Oh yeah, 8's tough.
Yeah.
I mean, well, the truth is it's not tough, but what makes it tough is sort of drawing the picture. I'm going to help you. I'll help you with 8. There's a moon. This is the moon, right? I think it says that I have a moon. So this is the moon. There is a center of the moon, but anyway, forget. All right. Then there's a satellite orbiting the moon, and it tells me that at its lowest point above the surface of the moon, it's, what does it say, 110 kilometers?
Yes.
So at its lowest point, it's 110 kilometers. And then this is an elliptical orbit. So then at its highest point above the moon over here,
Yeah.
it's 314 kilometers. But now this is not the best picture, but that's what's happening. The lowest point above the Earth, above the moon, and the highest point above the moon. Then it says the radius of the moon is 1728. So this would be 1728, and this would be 1728, because that's the center of the moon. See, it gets weird because I got the center of the moon, which is the center of this circular moon. This is the moon. And then I got this elliptical orbit around this circular moon. And so I've got this elliptical orbit, and here's the deal. When things orbit other things, the moon is at the focus of the ellipse. So the center of the moon is not the center of the ellipse. The center of the moon is the focus of the ellipse. That's sort of the main idea about orbits. You know, I kind of think I'm sitting there looking at the major axis. Do you agree?
You are.
Yeah.
And I'm very tempted to just add all that crap up.
Yeah.
Because that's the major axis. And one thing I know about the major axis, anybody know?
Divide it in half and find the center?
Well, I can divide it in half and find the center, and also because the length of the major axis is always 2a. mean, it's sort of a formula somebody told you or something you read, but it's also just kind of a fact. If you think about, you have the center, you go over A, you go over A. So the length of the major axis is 2A. You said divide by 2, you can find A and kind of figure out the center. I don't know how much that's going to help me. What am I supposed to be doing?
Find the equation of the ellipse.
Oh, I need the equation of the ellipse. All right, I'm going to assume, and so to do the equation of the ellipse, this is kind of from 10.1. This is not parametric equations, although we could do that, but it's just the equation of an ellipse, and I'm going to make the center of my ellipse 0, 0. So I'm not going to put minus h or minus k. And then what I really need is a squared and b squared, and that's kind of all I need.
Right.
So, I mean, to get the equation, that's all I need. And we just kind of talked about how to get a. So we said if you add all that up, that's the major axis, and that's 2a. So let's talk about that just real quick. So what add that up for me? What
You get 3,880.
3,880, that's 2a. So divide by 2, what's a?
1940.
1940, thank you. Cool, well, we're sort of halfway done with this problem. I mean, we want the equation of the ellipse. We just calculated a. You know, what often helps me find b is you got to have this thought in your head, you guys. When it comes to ellipses, remember a squared minus b squared is c squared. And then that's just a true fact for ellipses. So you might need that thought. And what is c? What is c? I mean, not the number, but what is c defined as?
The distance from the center to the focus.
Good, the distance from the center to the focus. Oh, so you're saying if I could find the center of the ellipse, then I could calculate that distance would be c.
I got 102 for that.
And you got 102. Now how'd you do that? You knew that a was 1940. So basically,
I took the add of the left side.
if you go 1940 away from that edge, you end up here, right? Or if you go 1940 away from this edge, you end up here. Oh, so maybe you add these up. What's that? 1828, 1838?
Yeah.
1838 plus a little bit will be 1940. And you're saying that little bit is 102. And it's funny, this problem's difficult, but it's adding and subtracting. I did do one division, so I did divide by 2. But so I'm not doing complicated math, but I am thinking of my way around this ellipse. And the center of the ellipse is here. The focus of the ellipse is the center of the moon. That's the thing that kind of throws you off. And the center of the ellipse is inside the moon, just like the focus is inside the moon. So we figured it out. I mean, I'm done. I did a little subtraction there. I found out c was 102. Now I can find b squared. I mean, that's what I want. I want a squared and b squared, and I'll have the equation of the ellipse. So we got it. 1940 squared minus b squared is the 102 squared, I guess. I guess you could move the b squared over and subtract this over, so then 1940 squared minus 102 squared is b squared. So now it's some huge number.
3,753,196.
That's b squared. It's this thing squared minus this thing squared. There it is. If you want to take the square root and find b, you could, but I don't kind of care. What I really want is b squared. So, you guys with me? That was fun. A lot easier than I thought. But, I mean, I know it's hard. I think it's hard for you guys. You're not used to thinking around. I guess I've thought, I've done these problems. You got to do a million problems. It all starts to sink in. That's 1838. That's what we did. We added those up. And so then the 1940 minus the 1838 left me with this. That's what I needed. I needed to find C. To get B. I needed to find C to get B. What else? Anything else?
Number 7. I didn't understand
Yeah. I don't know. Now, see, once I start helping you quite a bit, then I start not wanting to help you. But you still got till Wednesday. So maybe my mood will change by Wednesday.
These are 2 problems and like 1 that 4.
Can I say this about 7? Here's what I would like to say about 7. How far from the ultimate question is, how far from the vertex should you mount the receiver? And the answer is, you want to mount the receiver at the focus. And the distance from the vertex to the focus is P. So ultimately, this question is kind of find P. Right. Because, you mount the receiver at the focus, and the distance from the vertex to the focus is P. So you kind of want to find P for this parabola. And you don't know much about this parabola, but you have some data. You know this. You know that the parabola has this shape. And then I drew this shape that said it's 20 feet across, and it's kind of 8 feet deep. Now, by the way, then that 8 feet, you kind of maybe assume that's the focus, but don't assume that. I mean, this is just the dimensions of this satellite dish, and the focus could be anywhere in here. It could be here, 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 here. I mean, we don't know where the focus is. But the dimensions of the dish itself is this: 20 feet wide, kind of 8 feet deep, kind of, and that's the satellite dish. Man, the key is to throw this baby on an X and Y axis. That's the key. And you can stare at this forever and never think of that, but that's the key. Throw this on an X and Y axis. Oh, and put the vertex somewhere convenient. Like 0. Right. So I'm taking this picture now, and I'm doing this with it. And if it's 20 feet wide, then could you please tell me this X value? 10. And negative 10. And if it's 8 feet deep, so to speak, can you tell me this Y value? 8. And so can you tell me this point? Right. And so it's got a vertex of 0, 0. It's got a point there. I think you use that to help you find the equation of the parabola. And with the equation, I think you can find P. I think I'm just going to be quiet. I mean, this helps a lot. But you take this stupid generic picture and put it on an X and a Y axis with some coordinates, and then you'll fall right into it, I think. I want to do this problem out of the book. It's 22. And I'm in 10.5. I'm jumping up to 10.5. And it's 22. And it says this, because this will help you with one of yours on your... It says find the area between the loops. Between the loops of... So back to area and polar coordinates for a second. Find the area between the loops of r equals 2, 1 plus 2 cos. What did this say?
Sine theta.
1 plus 2 sine theta. All right, that looks a little strange the way they wrote that. I'm going to distribute the two. For most other problems, they didn't have it factored anyway. So this is the same thing, you guys. And maybe I need my graphing calculator in polar mode to kind of see what this is. But when they use this phrase between the loops, that implies that it's one of these limicons that has what we called an inner loop. And then, so anyway, that's what that implies. And so I kind of know what this is. It's one of these limicons with an inner loop. You know, earlier today I drew a couple limicons, but they were cardioids. They came into a point. They were little different limicons. This one will have an inner loop. If I plot points and draw a picture, kind of does this, comes in here and does an inner loop. You even see the inner loop?
Yeah.
Sometimes the inner loop's so small your graphing calculator doesn't draw it too well. So that's a rough picture of it. You know, but again, I would use my graphing calculator to help me get an idea, and then I'd kind of blow it up on paper is what I would do. But I want the area between the loops. So I've had that phrase confuse students. It doesn't confuse me at all. Do you? Do you think you know what area that means?
No.
The middle one.
I mean, between the loops. I mean, we call this the inner loop. I guess we call this the outer loop.
Yeah.
But nobody ever called it that, I guess.
So what?
So the area between the loops. It's obvious to me, but in other words, it's everything except the inner loop. I don't want that inner.
Oh.
The area between the loops would not be the inner loop, I guess.
Oh.
Well, I know. That's what I'm saying. Some students, that bothers them. I don't. But anyway, now you know. Between the loops means all this area. Damn. Okay. Well, that means I don't want that area of that inner loop.
So could you take the whole thing and subtract the inner loop?
Perhaps I do the whole thing and subtract the inner loop. Maybe that makes sense. You know, if you were going to do the whole thing, what kind of bounds would you set up?
0 to 2 pi.
0 to 2 pi. You don't even have to think that hard. Right. 0 to 2 pi does a limicon. So that would just do the whole thing. And then if you're going to try to subtract the inner loop, then you might want to know when does it do the inner loop? And I kind of wish you would tell me, but good. I want these tangents at the pole. I think I need these. See, they're called tangents at the pole. What they are, they're the angle when the graph comes in and does the inner loop. And then it comes back out. So I need these angles. And they're called tangents at the pole. Do you remember how to find them?
You have the r equals 0.
It's easy, right? It really isn't about tangent lines. In a way, it's about when is r 0? When does r go in and hit the pole? So when is r 0? So that's pretty darn easy, actually. Setting r equal to 0 and doing a little trig or algebra. So I want to find when r equals 0. So I set r equal to 0. I move the 2 over. I divide by 4. I get this negative 1/2. Negative 1/2 is very famous. That's 30 degrees. That's 30 degrees. Well, wait a minute. It's not 30 degrees in quadrant 1. It's 30 degrees
3 and 4.
in here and here. Let's see. 30 degrees here. Yeah, it's 30 degrees. That's 7 pi over 6, you guys.
Right.
This 30 degrees, I could call it negative pi over 6, negative 30 degrees, or I could call it 11 pi over 6. By the way, my picture doesn't really look like 30, does it? It looks like 45 or 60. Sorry about that. Should Should be more over here, but that's just my sloppy picture.
Does it matter if you 11 pi over 6 or negative pi over 6?
It does matter, kind of.
Okay.
Um,
How do you know?
like let's say you were just going to integrate from here to here. If you call this 7 pi over 6, then you want to integrate forwards to the next higher number, which would be 11 pi over 6. You would not want to say, I'm going from 7 pi over 6 to negative pi over 6. On a number line, that doesn't make sense. Are you with me?
Mm-hmm.
And on a number line, here's 0. And then here's 2 pi. You know, if I wanted to go from here to here, though, I think I would rename him negative pi over 6. I think I'd go from negative pi over 6 all the way around to 7 pi over 6. Just, again, I want my numbers to increase. My angles are numbers that I want. So it depends on the situation, but it does kind of matter what you call that when you're setting up bounds for an integral, right? But maybe I'm ready to sort of set this up. So what did y'all say? You said, just do the whole damn thing. That's what y'all said.
Whole thing.
Do the whole thing. Which means this, I'm integrating this function. It's squared, d theta. I'm going from 0 to 2 pi, and I got a half in front of it. Right, I mean, that's the formula. The function squared, half in front, 0. So you do the whole thing, but I don't want the inner loop. So now you're saying subtract the inner loop. Is that what you're saying?
Right.
Okay, I like that. I think I like that.
I think. So you'll go from 7
So now how do we do the what's called the inner loop?
7 pi over
7 pi over 6
to
to 11 pi over 6.
with a half in front.
Put the half in front and do the 2 plus the 4 sine theta. It's the same equation, you know, squared. But I get when the same equation with those bounds, you're doing the inner loop, like is what we figured out, right? It's the same equation.
Alright.
Again, I really don't want to do this one. Maybe I wanted to set it up, and maybe we're happy with this setup. Do the whole thing, and then subtract out the inner loop. And that'll be the area between the loops. All right, there's a problem with this. There's a problem with this.
Yeah.
And it's interesting. That's why I wanted to do this one. Okay, so to address this issue. This between the loops issue is kind of a funny issue because
What I had to do was subtract the inner loop again.
You did? Huh?
Yes, and I don't know
Well, she's
why
right.
that works.
Right. The correct answer is I got to subtract the inner loop twice. She
Yeah.
said she figured that out, I guess.
Yeah.
You got to subtract the inner loop twice. Can I explain it? Maybe. Let me think. If you're integrating from 0 to 2 pi, you're sweeping out these sectors of area. Look at them.
Okay.
So you're getting all this stuff you want, plus you're getting the inner loop.
Right.
Okay, now wait a minute. Okay, so if I go, look, I'm getting the inner loop. Oh, you know what? I'm getting the inner loop. You know, I'm getting the inner loop even if I just go from 0 to 7 pi over 6. Even if I thought I was not, let's not do this. Let's just go from negative pi over 6 and stop at 7 pi over 6. I'm still getting the inner loop. Then when I go from 0 to 2 pi, I'm doing the inner loop twice.
Yes, that's
It's hard to explain.
that's why it's subtracted.
Let me think. Here's how to explain it. Pretend you don't want the inner loop. Let's just go from negative pi over 6 to 7 pi over 6. Okay, good luck. Let's go from negative pi over 6 to 7 pi over 6. So when you think you're leaving out the inner loop, you're still sweeping over it. You're sweeping out these sectors of area and you're still getting it.
Right. Right.
Then when you integrate from 7 pi over 6 to 11 pi over 6, you're getting the inner loop. So when you do this thing from 0 to 2 pi, you're doing the inner loop twice. And if you're trying to subtract it out, then you probably should subtract out 2 of them.
So
that-
instead of 2 halves, maybe just have 1.
Well, I'm saying I better subtract out 2 of the inner loops because I did it twice here.
Yeah, 2 halves equal 1.
Oh, well, I never was doing a half. This was the entire inner loop. And now it's 2 inner loops. Why is the half there? The half's there from the formula.
Yeah.
But the bounds, look at the bounds. The bounds there tell me I'm doing the whole inner loop. I'm doing the whole inner loop. Now I'm going to do 2 inner loops and subtract them.
Because you went around.
Right.
So why did you have to go from 0 to 5? Why couldn't we have just gone from negative pi over 6, 7 pi over 6?
Okay, we could have. All right, so see that? Maybe that explains it even better.
Yeah.
All right, hold on. I went from 0 to 2 pi. My thought was let's do the whole thing and subtract the inner loop. So I went from 0 to 2 pi. But now this is confusing me, so let's start over.
Okay.
So now I decided, all right, damn it, I don't want to do from 0 to 2 pi. Now I'm going to leave out, I don't want to do the inner loop. So I'm going to go from negative pi over 6 to 7 pi over 6. That won't do the inner loop, right? I'm going to go from negative pi over 6 to 7 pi over 6. Now, that should start here and sweep out these sectors of area. Guess what? Even though I don't go plot those points, sweeping out this sector of area is still going to get that area that I don't want. So now I think I was leaving out the inner loop, but I'm still getting it. So what should I subtract now?
The inner loop.
1 inner loop, not 2.
Right.
Let's subtract the inner loop.
Wow.
I thought you left off the inner loop. Well, no. Hang on. The bounds left out the inner loop, but as you can see from the geometry of these sectors of area, I'm getting the inner loop even though I think I'm not. So I subtracted.
So doing it from 0 to 5 is completely unnecessary.
Well, doing it from 0 to 2 pi was actually it's kind of easy, but then it makes it a little hard for me to explain. But then I'm going to subtract 2 inner loops.
Right. That's why
To get the area
for me. I
between
couldn't
them.
figure out.
So it's one of the other those setups were good actually. Either one of those setups were good. But all right, I'm not sure what else you want to ask me. We got 10 minutes or so. I'm just going to hit pause here on this.